Okay, section 14.5 or 14.6, depending on which book you're using, talks about directional derivative and the gradient vector. A massive deal for us. Something that we're going to be using, and it's going to replace the derivative in 2 dimensions. Given that z equal f of xy, okay, to talk about a derivative, we talk about the partial with respect to x represent the rate of change in the x direction, and f sub y represent the rate of change in the y direction, ignoring everything else. That is in the direction of the I component and the j component. To find the rate of change of z equal f of xy, we find the directional derivative defined by f sub x, f sub y. This vector is used in many applications, so it has a name. We call it the gradient vector. The notation for it, gradient of f, delta f, or del f. This is really what you see, those two more than anything. In particular, this case. Note that f is a function by itself. You apply on it the gradient, and this is the gradient. The gradient is nothing more than an operator. It operates on a function by taking its partial with respect to x for the I, its partial with respect to y for the j. That's in 2 dimensions. In 3, it'll do it in terms of x, y, and z. A directional derivative enables us to find the rate of change of a function of 2 or more variables in any direction. Kind of like you finding the derivative of a function. The general derivative will give you just an equation that tells you the rate of change, but for a given value of x or t, you could find the rate of change at that specific point. I have an example to kind of refresh your memory on how this works and tie it to the gradient. So the gradient is nothing more than a traditional derivative for us, but it has some specific properties. So given x squared minus y minus 4 equals 0, we know what that is. That is really saying, if you move the y over, that says y equals x squared minus 4. That's a parabola. Sketch the graph of the function. Even though we're supposed to do that last, I could glance at that right now and kind of see how this looks. So I know it's going to be at 1, 2, 3, 4. Crosses at 2, 0, 0, 2, 0, and negative 2, 0. It's a parabola that looks like this. The point in question that they're really talking about is really 2, 0. Well, when x equals 2, obviously y equals 0. They're talking about this point. What they want us to do, they would like us to find an equation of the tangent line. Well, if this is the equation, then for I know that dy dx equals 2x. So this is like the general gradient function. This tells you the derivative, which could be the rate of change, but you need a point. This is in general. At different points, it will vary. At 0, it doesn't exist. At 0, it's right there. It's 0, really, not doesn't exist. At 1, it's a bit steep. At 2, at 3, and so on and so forth. I need it at x equal 2 specifically. So the rate of change is 4. Now that I have a value, now it makes, I could say the velocity is 4 of this function at t equal 2 seconds or 2 minutes. You know, I could now apply it to many things. Find an equation of the tangent. Well, equation of a tangent, y minus y1 equal m into x minus x1. So I could say easily y equals 4x minus 8 is the equation of the tangent. They say graph the tangent as well. Let's do that. 1, 2, 3, 4, 5, 6, 7, 8. Rise 4, run 1. Rise 4, run 1. If I connect this with a straight line, there's my tangent. So this is stuff that we already know, nothing new. Now comes the new stuff. Find the gradient. So how do you find the gradient? The gradient function is simply the partial derivative with respect to x applied on this, that would be 2x, and the partial derivative of this function with respect to y, it's right there. The partial with respect to x, the partial, that's f sub x, f sub y. And if it was 3 dimensions, f sub x, y, and z. No big deal. Again, this is the general gradient. That's like me saying the derivative is 2x. Well, without giving me a specific value, this gradient is just kind of like an expression that tells me, given those x and y, plug them in and I could tell you what the rate of change is. If I evaluate that at the point 2, 0, I'll notice that the gradient function turns out to be 4, negative 1. So if I go to the point 2, 0, the gradient is 1, 2, 3, 4, negative 1. The gradient is a vector. That vector is perpendicular to the tangent. So the gradient and the tangent are, I'm trying to get you to see what those mean and what those are going to find, because that's going to help you a lot as we move on. So sketch a graph of the function we did, the tangent and the gradient we did. What we notice that the gradient of f is perpendicular to the tangent. If I were to describe that as that's the graph for it, right? And everything else will match. So I noticed that the gradient is perpendicular. And one more thing I want to point out. If I look at the gradient, the change of I over the change in j over the change of I, right? That's the negative reciprocal of that. Now I want to show you something you already know but you never thought of it. Let me show you something. If I take the gradient and treat it like the vector back in my days. Which vector? The normal vector. The normal to the line. I'm talking about this line. So, to find an equation of a plane, I need a point on it. I got a point. And I need a vector perpendicular to it. The vector is right there. This is like my AB, if you remember, from back in the days. And the point is right there. What happens if I take A into x minus 2 plus B into y minus 0 and set it equal to 0? What would happen then? 4x minus 8 minus y equal to 0. And do you notice what the equation of this line is? That says y equals 4x minus 8. Do you see a connection between those? A bit confusing. Well, let me elaborate and clarify. If I was to tell you V is perpendicular to a plane and x sub 0, y sub 0, z sub 0 is on the plane. If you called V A, B, C, wouldn't you agree that A into x minus x sub 0 plus B into y minus y sub 0 plus C into z minus z sub 0 equals 0? Wasn't that on your first test? Well, let me show you a small secret. This demonstration is via GeoGebra. If I graph y equal x squared, it's right there. X squared minus 4. If I graph y equal x minus 8, there's the line. If I mark the point 2, 0, it's right there on the graph. That's where they intersect. If I go to the point 4, 0, if I go to the vector and I sketch it, it's right there. And I notice that those are perpendicular. Now, if I tilt this a bit, guess what? The line is actually the tangent plane to the curve. And the gradient is always perpendicular to the plane. In 3 dimensions, it's a plane. In 2 dimensions, it's a line. So when I go back to this is 3D, but this is the 2D of it, and that's why this works. That's why taking the components of vector A, of vector V, work just like it did before. So on 2 dimensions, there it is. On 3 dimensions, it'll be identical. So what we know, if you can get a plane that's tangent to the surface, the gradient is always perpendicular to that plane at that one point. And that's going to help us a lot in the remaining part of this section. And here we are. This is example 2. Changing direction slightly. Given f of x, y, which is z equal natural log of x squared plus y squared, and the point is 4, 3. Find the gradient. If I want to find the gradient of f, that would be 1 over x squared plus y squared times 2x, and 1 over x squared plus y squared times 2y. And if I substitute x, 4 plus 16, that's 25, and an 8, and a 6. There it is. That's part I. Got it. And if I proceed and figure out what, sketch the curve that passes through the given point, level curve. Okay, so what are you going to do? You're going to take natural log of x squared plus y squared and set it equal to some k, right? Normally you let k equal 1, 2, 3, but here you want it to pass through this point exactly. So that is what? That is 4, that's 16, plus 9, 25. So k is natural log of 25. So basically what you're doing, you're saying natural log of x squared plus y squared equals 25, equal natural log of 25. Or simply, again, remember the level curve, the contour graphs, or simply x squared plus y squared equals 25. So a level curve, specifically they want one that satisfies this equation. If I am to move the graph would look something like this. There. The point 4, 3 is right there. And if I am to look at my vector would be from this point 8 divided by 25. So in the I direction and in the j direction, this vector right here, if you can imagine a tangent line, it would be perpendicular to it. Again, I want to demonstrate graphically what I'm doing. So graphically, if I look at this, if I am to look at a graph, there's a circle with a radius of 5. If I really throw at it the point, let me see where I put that. 4, 3 is right there. And if I draw my vector, the one I just found, it wouldn't be that big, but I extended that so you could see it. Now, if I want to find an equation of a tangent, this is what I'll do. I could say, take this to be A and this to be B. Now, any multiple of those will do, so I could multiply by 25 if I want and make them 8, 6. It doesn't matter. Any extension of that would still be perpendicular to this line. So I could say 8, 6 if I really wish. It really doesn't matter, or leave it as 8 over 25. I could say my vector in 2 dimensions is really this, and my point is right there. And I could say 8 over 25 times x minus 4 plus 6 over 25 times y minus 3 equals 0. If I sketch the graph of this line, guess what I will get? That line right there. I'll get the tangent line, even though it's kind of annoying to think in terms of a tangent line. Well, that's because I'm really shrinking down the dimensions. What I'm not telling you is that this graph is really 3 dimensions. If I tilt that a bit, guess what? This is a sphere. I was looking at it from the xy, really yz plane. But if I tilt it, it's a sphere. What I know, if there is a tangent line, the gradient is perpendicular to the tangent line at that one point every time. And that's going to help me a lot toward the end of this section and next entire section and later on. Because if I find the gradient of f and I set that to be a, b, c, sort of my v in chapter 12, and I'm given a point x sub 0, y sub 0, z sub 0, guess what? A into x minus x sub 0 plus b into y minus y sub 0 plus c into z minus z sub 0 equals 0 will give me the equation for the tangent plane, right, to the actual 3-dimensional surface. And that's a big deal for us. I'm going to stop this video. This video is only to explain and connect things together, really. I didn't need to graph the tangent based on example 2. I just need to graph the gradient and make sure to go from the point, the actual point, and sketch the gradient. Even though if you go from the origin, it would still work because it's an extension of that. But you're supposed to go on it. On the surface, the gradient is always perpendicular to the tangent. If it's 2-dimension, the tangent line, and if it's 3-dimension, the tangent plane, which means I could use my gradient as my perpendicular vector to the plane at a given point and find the plane backwards. So this is it for this video. The next video I'm going to go more into what the book wants, and I'll be